Welcome to the 7th module of the E-Pathashala program lecture series on computer science for the compiler design course. So, we start with the example which we were constructing a DFA from a regular expression, which is a minimized DFA. So, we will continue that example and finish it before we move on to the other approach to constructing a minimized DFA. So, what we did was we have to construct the root of the tree. The root is here. This has the first position as 1, 2, 3. So, that will be the first node. And now what we do is we look at these numbers in the tree and find out which node numbers correspond to the character A and which correspond to the character B. So, here 1 and 3 corresponds to A. So, we should look at the follow position of 1, 3 and make an edge from this node on A to a new node which has got the follow positions of the union of 1 and 3 respectively. So, which is follow position of 1 is 1, 2, 3, follow position of 3 is 4. So, I have a new node here which has got a number as 1, 2, 3, 4. Similarly, for this particular 3 index numbers 1, 2, 3, so 2 corresponds to the node B. So, we have to look at what is the follow position of 2, which is 1, 2, 3 again if you remember. So, we have to have an edge from here to 1, 2, 3 on the input symbol B. Similarly, from this node we have to look at which nodes correspond to A. Again here 1, 3 corresponds to A. So, from these nodes follow position are the union of these nodes follow position are 1, 2, 3, 4. So, I have an edge from here to here on A. On the other hand 2, 4 has a follow position as corresponds to the character B. So, 2's follow position is 1, 2, 3, 4's follow position is 5. So, from here on B you have a new state numbered as 1, 2, 3, 5. Similarly, from this particular node again 1, 3 corresponds to A. So, follow position of 1, 3's union is 1, 2, 3, 4. So, from this node I have an edge from here to here on A. Similarly, 2 and 5 corresponds to the node B. So, its follow position will be 1, 2, 3, 6. So, I have a edge from here to here on B and have a new node which is 1, 2, 3, 6. Again from here on B I have this corresponds to only 2. So, 2's follow position is going to be 1, 2, 3. So, I have an edge from here to here on B. Similarly, 1 and 3 corresponds to A. So, I have an edge from here to 1, 2, 3, 4 node on A. Now, how do I mark the final state? The final state is marked such that whichever node has got the follow position as the number corresponding to the hash node. So, I have a hash node here whose number is 6. So, that is going to be your final state. Now, this is your minimized DFA. If you remember, we had a 5-state DFA as against a 4-state DFA, which is a minimized one here, where we converted from regular expression to DFA directly. Now, the next algorithm which we are going to see is the table filling minimization algorithm. That is the objective of this particular module, where we are going to construct a DFA and then use a procedure to eliminate redundant states. And then this was actually already done, construct the DFA directly from a minimized algorithm, which has already been discussed. Now, the basic idea is to find all groups of states that can be distinguished by some input string. Now, I will say that 2 states are distinguishable. Okay. When I say distinguishable, these states are not equivalent. Now, if there is a non-equivalent state, that there should be a equivalent states. Okay. So, non-equivalent is easy to find out. So, we will use that concept rather than looking at the equivalent concept. 2 states are non-equivalent if one is accepting and the other one is a non-accepting state. Okay. So, that is how we call it as a non-equivalent. Non-equivalent basically means it is going to be distinguished pair of states. So, what do we do is we assume 2 distinguished groups of states. Okay. So, given an automata, remember that this automata has got more number of states and our aim is to minimize the number of states of the automata. So, what we do is we form 2 groups. The first group is a group of non-accepting states and the second group is a group of accepting states. So, this is a very simple logic. We will just break this into 2 groups, one is accepting, other one is non-accepting. Then we use the method of partition of equivalent class on input string to partition the existing groups into smaller groups. So, we keep on partitioning that. Okay. So, how do I partition? So, this is going to be the algorithm here. So, an input will be a DFA M, which has got a set of states S, a input symbol sigma, a transition function move, a start state S naught and a set of accepting states F. Output will be a DFA M dash accepting the same language as M and having as few states as possible. So, what do we do? So, construct an initial partition pi of the set of states with two groups, the accepting states F and the non-accepting states S minus F. So, pi naught is equal to I01 to I02. Okay, I have two groups here. For each group I of pi I, partition I into subgroups such that two states S and T of I are in the same subgroup if and only if for all input symbols A, states S and T have transitions on to states in the same group of pi I. Okay. Replace I in pi I plus 1 by the set of subgroups formed. That is, supposing I have two states in a particular group to start with. For all input symbols, those two states should go to only itself. For example, if I have, let us call, I have two states here, A comma B. Okay. I have input symbols A comma B. States, let me call this as 1 comma 2. Okay. So, 1 on A should go to either 1 comma 2, 1 on B again should go to 1 comma 2, 2 on A again should go to 1 comma 2 and 2 on B also should go to 1 comma 2. Even if there is going to be one distinguishable scenario, I have to break this into two groups. That is the fundamental. So, if pi I plus 1 equal to pi I, let pi I final is equal to pi I plus 1 and continue with the step 4. Otherwise, repeat step 2 with pi I plus 1. Okay. So, this is your step 2. Let us take this, choose one state in each group of the partition pi final as a representative for the group, which are the representatives will be the states of the reduced DFA M dash. So, after that we will find out one small subgroup and then decide on which will be your states of your DFA, new DFA M dash. Now, let it S and T be representative states for S and T's group respectively, and suppose on an input A there is a transition of M from S to T, then M dash will have a transition from S to T on A. So, I will explain this with the example when we talk about it. Anyway, what we say is, supposing I have 1 comma 2 as one state, okay, 1 comma 2, let us say I am not able to break this group at all any further, okay. I will choose either 1 comma 2 only, and then let me call this as 1, which means that 1 and 2 are equivalent, which means I am not able to break this further. That basically concludes that 1 and 2 are basically equivalent states, they are non-distinguishable states. In that case, I will replace either 1 comma 2 with either 1 or 2, okay. Call this as 1, this is going to be 1. So, wherever there is 2, I replace that with 1, okay, and 2 will no longer exist, that will be replaced with 1 only in your new DFA M dash. That is what it basically tells you. If M dash has a dead state, a state that is not accepting and that has transitions to itself on all input symbols, then we have to basically remove it, okay. Non-accepting means that is, it is not going to be part of your final automata at all. Also remove any states not reachable from the start state. This is a very important point. We will call that a particular string belongs to your automata only if I can go from the start to the final state. If it is not, I will basically remove that. So, basically here what we say is, if supposing a particular state is not reachable from the start state, you need to remove that, because it is not going to be taking part in your generation of string. This means, the meaning that string W distinguishes state S from state T is that by starting with the DFA M in state S and giving it input W, we end up in an accepting state. That is what we basically talk about as distinguishable states, okay. So, this is what we already said. Starting in state T and giving it input W, we end up in a non-accepting state or vice versa. So, then you can call these two states as distinguished states. Let us take this example. I have a state 0, 1, 2, 3, 4, 5 and 6. This is going to be a DFA which is constructed from a regular expression which is being derived to an NFA and then to a DFA. So, I have got here 3 states which are non-accepting, and I have here 4 states which are going to be accepting, 3, 4, 5 and 6. Now, what is my first group will be, I have to group 0, 1, 2 into one group, I have to group 3, 4, 5, 6 into another group. So, I am going to form 2 groups here, 0, 1, 2 and 3, 4, 5, 6. So, the first group will be 0, 1, 2 and the second group will be 3, 4, 5, 6, because 0, 1, 2 are non-accepting and 3, 4, 5, 6 are accepting. Now, let us consider the non-accepting states of pi naught. Now, 0, 2 on A will take you to 1 and 1, A will take you to 3. Okay. So, 0, 2 on A takes you to only 1, if you remember that, 0, 2 on A takes you to 1, okay, and 1 on A takes you to 3. So, what did we say about the grouping? 0, according to us, if I should not break this, 0, 1, 2 on A and B should basically go to only itself, okay. But I am able to see a first distinguishing characteristic where 0, 2 on A goes to only 1, whereas 1 on A goes to 3. So, definitely 0, 2, 1 should not be in the same group. So, let us try to break this into 2 groups, 1 separately and 0, 2 separately. Now, 3, 4, 5, 6 I am not touching upon it now, because 3, 4, 5, 6 will be our accepting states. Now, again with reference to this, we already know 0 on B goes to 2, whereas 2 on B goes to 5. So, 0 and 2 also should not be in the same group, okay. So, that is going to be our next split. So, I am going to break this into 1, 0, 2 separately, okay. So, this is your first split. So, I have basically jotted down on how the non-accepting states should be split. So, I cannot group the non-accepting states at all in this particular scenario. Take the accepting states 3, 4, 5, 6. Now, 3, 4, 5, 6 all on A, 3 on A goes to 3, 4 on A goes to 6, 6 on A goes to 3, 5 on A goes to 6. So, 3, 4, 5, 6 is a single group. So, all these states on the input symbol A goes to only itself, okay, it is not deviating. Similarly, if you consider 5 on B is 5, 6 on B is 4, 3 on B is 4, again all of them either go to 4 or 5 respectively. So, therefore, 3, 4, 5, 6 will be in the same group because all of them go to either 3, 6 for A or 4, 5 for B. So, therefore, I have 1, 0, 2 and 3, 4, 5, 6 as one group. Now, this is what I said, 3, 4, 5, 6, this is one set. I could call this with a single number, and wherever the other numbers are there, I could replace it with only one number. So, apply the same step again to pi 1 and get pi 2. That is what we have got here. Pi 2 is 1, 0, 2, 3, 4, 5, which is equal to pi 1. Since I have the same number, I say that this is going to be called as pi final. So, you have to keep on doing until you are not going to get any new group. So, let us now say I am going to represent this state, this group with the number 3, okay. I can call it with any number, I am just calling it with number 3. So, how does it look like? Now, 0 on 1, so I have only one final state now. If you remember, 1 on A was 3, but 2 on B was 5. If you remember the automata, 2 on B was 5, okay. Now, what happens? 2 on B will also be the same state 3. Similarly, 3 on A is 3, 3 on B is 4, okay. But now it will be the same state with number as 3. So, this is what we talk about as the minimized version. So, where I had almost 7 states, I have now minimized it to 3 states. So, 0 on A is 1, 0 on B is 2, these 3 as it is, I am not disturbing that. 2 on B was 5, now it goes to 3, 1 on A was 3, same 3, 3 on A is 3, 3 on B was 4, now it is the same 3. This is going to be your minimized DFA. Now, what we have done so far is, we have got, we have defined patterns, okay, to accept a particular token. Now, given any token, I will make it pass through a DFA or an NFA or a regular expression and check whether the string matches the given pattern. Now, how do I get input? Now remember that our overall input is going to be a source program which is in C or C++ or Java or whatever it is. Now that I will have so many strings, okay. So how do I recognize token? We already know that your job is to match it with a pattern and assign a token. You will get the lexeme. Now getting the lexeme, we have to define a pattern. That is what we have basically done. After that, we have to assign a token to the lexeme. So the task of token recognition is in lexical analyzer depends upon, you have to isolate the lexeme for the next token in the input buffer and produce as output a pair consisting of the appropriate token and attribute value such as ID comma pointed to the table entry and using the translation table. So this should basically be constructed. So I have here ways of defining patterns for recognizing a lexeme. After that, what do I do? That is what we have basically remember. If you remember in one of the modules, we already said that if it is going to be a token called as if, I followed by f will have a final state there, and there I will return if comma keyword. Okay. So that is how we have to basically construct this. So how do I get input? How do I then process it is what we are looking at here. So this is what we have to basically say. Regular expression for the token if will be I followed by f, and it will not have any attribute value, or it can simply have a keyword. Regular expression for a variable identifier will be, I will define it using depending upon the programming language, and then I will assign the token as ID, and then the attribute value will be the pointer to the symbol table entry. And if I see a regular expression as less than, I will assign the token as relational operator, and the attribute value will be LT, less than. So this is how I had to basically assign it. Okay. Now this can basically be done using two concepts. One is called as the input buffering, where I will say it is a 2 buffer input scheme to look ahead on the input and identify the tokens. So I have an input, I will put it into a buffer and then keep on determining the longest matching pattern. So for that we have two ways. One is called as buffer pairs, other one is called as sentinels. Buffer pair is something like this. Okay, this is again from the textbook on Ahosethi-Ullman. Supposing I have a expression E is equal to MC squared. So I will get this in my buffer, E space equal to space M star C double star 2, and then there is, it's over. So I have a end of file marker there. Now I will have here two pointers. One is called as the forward pointer and the other one is called as the begin pointer. At any particular point of time, to start with, both will be at the same position, the forward pointer and the begin pointer. The forward pointer will keep on moving, okay, until it finds a longest matching prefix. So I have a E, it keeps on moving, I find an equal to. It knows that equal to is going to be not part of a identifier, so it stops here, and distance between the forward pointer and the beginning pointer will basically correspond to the identifier E. If you remember that, again here is equal to. After that I will have M, okay, I will then have only star, I will then have only C. At one particular point my forward pointer will be here and my begin pointer will also be here. It keeps travelling, it does not stop here, it looks at the double star, then it finds it is going to be an exponentiation operator as against a multiplication operator, because it is going to find the longest matching prefix. Okay. So that is how it basically identifies all the tokens. So you put it in the input buffer. Now what is the drawback with this? The drawback is, supposing I have a longer naming convention. Okay, I have a longer naming convention and this is going to be split in, this is a buffer is typically split into two halves. What if it overwrites? It goes to the next half. Typically what happens is, I have a half here, I will have one more half here. Okay, I will keep on filling this buffer first. Once I cross this pointer, I will refill this buffer. So supposing my begin pointer is here and my forward pointer is first character, this will be overload, this will be refilled. In the process of refilling, I would have lost my begin pointer. Okay. So, what happens is your buffer is typically split into two halves. That is what we, if you remember the previous slide, it said two buffer input scheme to look ahead on the input and identify tokens. So, you have two halves, the first half will be filled, and then supposing on a particular scenario, my begin pointer is here and the forward pointer is here, I will have to find out the difference between the forward and the begin pointer. This will be my string. But what happens in one condition is, if it goes beyond the half, this half of the buffer gets refilled. In the process, I will be losing my begin pointer. So, therefore, to avoid this, what we have is, we have what is called as sentinels. Sentinels are nothing but guards. They act as guards to guide end of file marker at the end of each buffer half. So, what happens here is, after every buffer half, what we do is you put an end of file marker here, and so I will know that I have to be cautious and it will not be filled up till the end. Okay, I will just put some end of file marker in the middle itself, and then I will, even if I reload this, it does not have any problem. I can go to the other half and then get my input as it is. So, these two schemes are for processing your input. So, what happens, your input is in a file, it puts into the buffer, it gets this string. How does it get the string? By matching it with the automata or your regular expression and assigns a token to it. So, this is the overall scenario, overall flow of your lexical phase. It gets the input, puts it into the buffer, of course with all the guards and markers and stuff like that, and then it will try to capture the string between the forward pointer and the beginning pointer. To capture that, it uses the pattern which is defined using your automata or your regular expression, gets the string, and then whatever attribute you have already put it in the automata, it will assign the attribute correspondingly. Now, that is the overall work of your lexical phase, and in the process what happens is, if it finds there is going to be an error, if it does not match as a pattern, it is going to say it is going to be an error. Okay. Now, if it does not match a pattern, what will it do? There are actually lexical errors typically are handled using what is called as the panic mode of error recovery. Now, you typically have two modes of error recovery. One is panic mode, other one is called as the phrase mode. Now, this panic mode is very similar to how we react to a situation. Supposing, say, you spill water on your dress, you immediately try to get up or do something such that the water does not get deep into your dress. So, that is the exact scenario what this lexical panic mode of error recovery follows, where supposing it finds a non-matching thing, it can do one of the following: delete, insert, replace or transpose. Deleting an extraneous character, which means that supposing if I have an extra equal to, okay. So, I am supposing I am going to have AB equal to, it is going to delete the equal to character there and say, okay, AB could be your identifier, okay, or it could insert a missing character. Supposing, say, I have got AB space K, okay, equal to 5, okay, if I have something like this, AB space and then a K equal to 5 or equal to 7, whatever it is, okay. This is my scenario. It knows that this is not going to be qualifying as an identifier. So, what it can do is, it can insert some number here, 1 or an underscore. A valid character could basically be inserted, okay. So, that can be happening such that it is not trying to fix your error, it is just trying to correct the error such that it can proceed with the compilation process, okay. So, it is not trying to fix an error for you, it may be correct or incorrect, we do not know, but it is trying to simply fix the error so that it can proceed with the compilation process. The next one is replacing an incorrect character by a correct character. For example, if I have again int a, okay. In the process, supposing if I had it as k a, okay, it can replace this k with a t just by guessing, okay. Probably all you might have meant it in a different way, but it would try to simply fix it in some particular fashion. either delete or insert or replace. The last one is transposing two adjacent characters. Okay. That is, this is a typical typographic error. We normally, in a typing speed, we will normally say fi for if. Okay. So, in that case, it will try to fix up this by swapping two adjacent characters such that it can basically proceed with the compilation process. Fi would probably not make sense, but if would probably make sense. Therefore, it is going to go ahead with the compilation process. Or you can do it with the pre-scanning, where you can try to look at it in earlier stage itself and then try to fix your errors. Okay. So, of course, but these four are the normal and standard procedures for fixing up the lexical errors. Okay. To summarize here, we have basically constructed the DFA in two ways, one directly, other one indirectly. The indirect construction basically results in so many number of redundant states. The indirect construction is from the RE, you construct the ENFA and then to DFA and then minimize it, which is using what is called as a table filling algorithm. And the next one is constructing a DFA directly from the regular expression, which is going to be using your syntax tree construction and finding out nullable positions, nullable last position, first position and follow position. So, with that you have the construct of the DFA. Now, to summarize on the lexical phase, we have basically got the pattern in terms of the DFA or NFA or RE, and we already have the input which is put into a buffer, and from the buffer you try to use two pointers to find out the longest matching pattern. How do I match the pattern? Using the constructed DFA or NFA. Okay. Match the pattern and then decide upon the longest matching string, and then that will be used for identifying and assigning a corresponding token. So, that completes your lexical phase. Of course, there is a shortcut to this, which is called as lexical analyzer generator, which is done in the, which will be done in the next module. Thank you.